Hey, welcome back. Today we're going to be talking about periodic trends and how to reason through problems that you might have for periodic trends. So maybe you're a chemistry student or a physical science student, integrated science student, and you have questions like, which atom is bigger and how would you know? Or which atom has a greater ionization energy? Or which atom has a greater electronegativity? I'm going to show you examples of how to reason through this in a very quick and hopefully useful way using some just basic ideas of attraction and repulsion. So let's go ahead and get to it. Now at this point in your education, I'm assuming you're familiar with what a Bohr model atom is. And it's a useful way of showing an atom. It's not really the most true way of showing an atom, but it's a good stepping stone to get to better understanding of how atoms are structured. If you don't know what a Bohr model atom is, I'll put a link to the right in the upper right about now if you want more background information, but let's go ahead and take a look at this. So the Bohr model for magnesium is drawn on the left, and for chlorine is drawn on the right. So these are two atoms that are in the same period, and so that means they're in the same horizontal row. And so you could say, well, what's the atomic size? So what I want you to do is I want you to think about these valence electrons and think about what the relative strengths of the forces are on an outermost electron. So there is an inward force and there are outward forces. So let's talk about the inward force first on these valence or outermost electrons. So first of all, there is an attractive force inwards, and that's from the protons in the center of the magnesium atom. And so we do have an inward force. I'm just going to draw with a red arrow like this. And it's an inward force because opposite charges attract. So the negative electron is attracted to the positive protons. That is true. Now let's do a valence electron for a chlorine and think about it. Now check this out. What do you think is going to be true about the inward force of chlorine versus the inward force for magnesium? Which is going to be greater? Well, the inward force for chlorine is going to be greater because it has 17 protons. Magnesium only has 12 protons. So that means I'm going to represent this with a bigger force going inwards like this. And I represent a greater force with a longer arrow. By the way, a force is just a push or a pull. Alright, now we can say there is a outward force on these valence electrons as well. And that's because electrons repel other electrons. So they're attracted by the protons in the center of the atom, but they're repelled by filled shells of electrons underneath the valence electrons. So for every filled shell of electrons we have, there is a pushback. So there are two filled shells on the valence electron for magnesium. So I'm going to draw two pushback forces signifying two pushbacks from the two filled shells underneath the valence shell that we are working with. And how about the chlorine? What do you think over here? How many filled shells underneath the valence electrons do we have? Well, we've got two filled shells underneath it. So we still have, in a relative sense, the same amount of pushback. So it's still being pushed back, like there's still some repulsion on that valence electron. We still have the same amount of repulsion, but we have different amounts of inward forces. So let's start comparing them. Now, if we compare the outermost forces, like we have right here, these are the same. And if we do a relative comparison, something that is the same, I mean, that's important to note, but it's not going to answer the question of which one is bigger. So far, we can't tell that there's a difference. Now let's take a look at the two inward forces over here, these two forces, and I want you to notice that these two are different. And so if we do a relative comparison problem, really all we need to do is focus on the differences between the two things that we are comparing. And so that's what we're doing here. We're saying that the inward force is greater for chlorine. And if we understand that, then we can answer all three of the periodic trends. So let's go ahead and give it a shot. When it says relative atomic size, okay, so is magnesium bigger or chlorine bigger? I want you to pause for a second if you choose to and think about this. Which atom would be bigger? What do you think? Okay, well, you may be tempted to say that chlorine is going to be bigger because it just has more stuff on the right-hand side, but it turns out that's not true. I want you to think of chlorine as being smaller and tighter because it has a greater inward force. So that means the relative atomic size for chlorine is actually less, which also means as you go from left to right across the periodic table, the atomic size shrinks. The size of the atoms literally gets smaller. You could also have a question that uses the term atomic radii instead of atomic size. All right, so that means the relative size of magnesium is actually bigger than chlorine, right? Like magnesium is bigger than chlorine is what we're saying. Let's compare ionization energies. What is ionization energy? Well, it's the amount of energy it would take to rip an electron off of the outermost shell of the atom. So if you take a look at magnesium, notice again, the inward force is just not as great. With 12 protons, the inward force is not as great as chlorine, where the inward force is much greater. And so as a result, chlorine is holding on to its outermost electrons more strongly. It would be harder to rip an electron off of chlorine. So what we're going to say is the relative ionization energy is greater over here and lesser over here. It's easier, in other words, to take an electron off of the surface of magnesium, a valence electron off of magnesium. And let's compare electronegativity finally, which are third trend that we need to talk about. And for this, I want you to imagine a free electron in the middle between the two atoms. And the question is, which direction, if you just set a free electron that is somehow motionless, equidistant from both atoms, what direction would that electron go? Okay, well, I want you to think about this. Well, this free electron would actually be more attracted to chlorine than it would for magnesium. And again, it really comes down to they still have the same amount of repulsion, basically, to free electrons, but chlorine has a greater pull, and so it's more attractive, or you could say more electronegative than magnesium is. So we're going to say this is an increased or a higher amount of electronegativity, and this magnesium is less attractive to free electrons or has a lower electronegativity. All right, let's use the same strategy now to go down the periodic table and see what happens there. Okay, and so taking a look down the periodic table, comparing what's happening there, let's think about, again, same strategy. Let's think about first our pushback. Here we've only got one filled shell underneath a valence electron for beryllium, whereas for this one right here, we actually have two. We've got two filled shells underneath that valence electron for magnesium pushing back, and so there's more of a pushback on those outermost electrons, and so that's something important to note. And then lastly, our inward attraction, yes, this is going to be smaller and this is going to be greater over here, but now we need to talk about something else that's going on as well in terms of the physics of chemistry, so to speak. And I want you to think back to your own experience. Have you ever played with magnets before? Hopefully the answer is yes. You can feel the attraction as the magnets approach each other, or if one of those magnets is flipped in an opposite direction, you can feel the repulsion. And notice that as you bring those two magnets together, the force gets greater. Either attraction or repulsion between them gets greater the closer the magnets are to each other, and lesser the farther they are away. Now, this is similar to magnetism. It's not exactly the same thing, but in this case, the negative electron is attracted to the positive protons. And yes, there are more of them, but they're also farther away. These are farther away. So let's keep that in mind. Let's talk about a couple of ideas here. We can say that the relative atomic size, so the atomic size, this is just going to be smaller and this is going to be bigger. And hopefully that makes sense. There's more pushback on the outermost valence electrons. So it would make sense that, like for magnesium, there's more pushback. So that would make sense that magnesium, to say, is bigger. You could also just say there's just more stuff here. There's more layers. If you're going to add more electron shells, then you would expect the atom will be bigger. Relative ionization energy. Now, this is where the distance concept that I had talked about really comes into play. If the magnets you're playing with when you were a kid are farther apart, remember that force between them gets much, much, much less. It's an inverse squared relationship, so it means it's much, much, much less. So as a result, the bigger atoms, they hold on to those outermost electrons more loosely, you could say. So what that means is this ionization energy for magnesium, this is a bigger atom here, it takes less energy to strip an outermost electron off of the surface of magnesium, whereas this is going to be greater because the outermost electron is closer to the proton here. So even though you could say the attractive force is less in the sense of having 4 protons versus 12, that's true, but it's still just a fact of the distances involved for magnesium are greater, so those outermost electrons are held more loosely. Lastly, let's do our electronegativity test, and just imagine we have an electron, let's say right here, in between, and it's just placed motionless between the two atoms. In what direction would it go? Well, it would go towards the beryllium, believe it or not. And this may be tough for you to think about again, because you might just think, well, look, there's 12 protons here, so it's just going to get attracted. It is true, there's a greater pull towards the magnesium, but there's also more pushback from the magnesium. So keep that in mind too. There's more pushback from the magnesium, and this electron is trying to find a spot at a point that's farther away. This is a farther distance, this is a smaller distance. Smaller distance between the valence electrons and the charge. That's like bringing two weaker magnets really closer together. They can still have a significant force if they're brought close enough together, right? That would be like the beryllium example. So it turns out that the electronegativity as you go down the periodic table actually goes down. This goes down, and it's greater as you go up the periodic table. So that's just how to reason through and think through some of these ideas. Hopefully that's been helpful. If you have any questions or comments down below, please let me know. And I hope you all have a great day. Take care.